Hello friends, welcome to Susan and John MathTube. We are going to continue our discussion based on areas in polar coordinate system. The last video was a small one, but I gave you a clear-cut idea how we find areas in the polar coordinate system. So I'll repeat that for students who did not watch that video. So look at this. What we have is the polar coordinate system, that is, we have the pole and the initial line. Okay, now what we do is we have a function r is equal to f of theta, and of course functions will have a graph, and let's say this is the graph. And now look at this. I'm interested in the area between these two radius vectors, and that means I want this much area. Okay, and let's say this angle is theta 1 and this much angle is theta 2. So the required area will be 1 by 2 integral of course theta 1 to theta 2 r square d theta. That is exactly what we learned in the last video. In today's video, what we do is we will learn how to calculate the area of some standard equations. Anyway, I have a graph plotting software over here, and I need this tool so that I can show you a few pictures. So look at this. I'm trying to plot r is equal to constant. I'll show you what will happen if you plot this. I have a rough idea. I'll do that first and then we will plot. So look at this. I told you in the last video, every point will correspond to r and theta. So for example, if I input the value theta equal to 0 degree, the r value is A. If I input theta equal to 90 degree, the r value is A. If I input 30 degree, the r value is A. So I think you're getting what sort of picture we are expecting. It's a circle. It's a circle with radius A. Now let's confirm it. So let's use this software and try. So I'm going to type some number here. R is equal to 2. And let's check the display. Okay, so look at this. See, a circle with center origin. Actually this is a combination of Cartesian and polar coordinate system. You can see the polar coordinate here, but they have merged it with the Cartesian system, and you can see every point they are measuring radian measurement. So look at this, 2, 0, it starts with 2, 0 degree, and they keep on moving. Okay, so we have a circle. So I want you to plot the first thing, or I want you to note the first thing, that is r is equal to A, is a circle with center, pole and radius A units. Okay, so let's do one problem with that. The question is very simple. Find the area of the circle r is equal to A in the polar coordinate system. So what we do first is we draw the initial line, and of course we will mark the pole. Okay, we have the initial line and the pole. And what is r is equal to A? Yeah, a circle. And I told you the logic behind it. You put any angle, we get A, so 0 degree, 30 degree, so a circle will be generated. And what will be the radius of the circle? Yeah, A units. So this is the angle 90 degree, and this is our 180 degree, and this is our 270 degree, and of course 360 will be 0 itself. Now it looks like the Cartesian system, but please mind it, it's not the Cartesian system. Okay, so look at this. By symmetry, I'm going to write required area is equal to 4 times the shaded area. I'll write like that, shaded area. I'll shade it properly. And I forgot to write the equation. So what's the equation of this circle? R is equal to A. Okay, and now I'm going to use the formula I taught you in the last class, half integral r square theta. Now look at this, we have to measure this angle. So look at this, we have to measure this angle. So this is 0 degree. Can you see? This is 0 degree. 0, 0, 1, 20, 30, 40, 45 degree, and it goes up to 90 degree. I think you're able to see that. I'll repeat once more. We start with 0 degree and move on 45 degrees, maybe 60 degree, 70, 80, 90 degree. So that is clear. So theta varies from theta equal to 0 to pi by 2. Yeah. And this will be, these two will get cancelled. 2 times theta equal to 0 to pi by 2. What is the r value? In Cartesian system, I was asking the question, what is the y value in terms of x? Likewise, here I am asking, what is the r value? A. So r square is a square is a constant, it goes outside, d theta. So 2a square, theta within the limits 0 to pi by 2. Now plug in the values, you get 2a square pi by 2. Yeah, we get the same answer, pi a square, as expected, because the area of a circle is pi r square. Okay, now let's move on to a little bit complicated curve, and please note the curves. One is r is equal to a into 1 plus cos theta, and another is r is equal to a into 1 minus cos theta. These are called standard cardioids. What do you call the curves? Cardioid. Where have you heard this name? Okay, heart related things. Okay, I'll plot one cardioid for you. So I'm going to plot 2 times 1 minus cos t. See, this is the cardioid. So remember, we have our initial line here, and then it goes on like this. This is actually the shape of the cardioid. R is equal to a into 1 minus cos theta. So look at this, it looks like a heart. Okay, so you can note these things. R is equal to a into 1 minus cos theta is a cardioid. And you saw the shape of the cardioid. So we have our initial line, and the cardioid looks something like this. It will be towards this side. I'm not that good in drawing, but you saw the picture already. Okay. And the next thing you can write, r is equal to a into 1 plus cos theta. So similarly, this will be a cardioid in this direction. It will go like this. Please make sure you draw properly. Okay, that's it. So now write one question. Find the area of the cardioid. R is equal to a into 1 minus cos theta. So the first thing to do, as always, you have to make a rough graph. So I take the initial line, and now I have to plot the pole, and then we go for the rough picture. It will be towards this side. Okay, and it's a symmetric picture, so I can draw and join this. Okay, it should be proper. Okay, now look at this. I'll take a pointer, a line, so that you can see the angles. So look at this, 0 degree, it goes like this. So this is 90 degrees. I'll mark 90 degrees, and I'll use another color. And look at this, 0 degree to 90 degree, 90 degree to 180 degree. So you can see that 180 degree. And I want to tell you one more thing. This is a symmetric picture. That means the area above the initial line, this is our initial line, the area above the initial line is equal to the area below the initial line. So please write required area equal to 2 times area above the initial line, and that will be, what's the formula for area in polar coordinate system? 1 by 2 integral r square d theta. And I'll take my radius vector. So look at this, the radius vector starts here. Can you see the blue line? 0 degree. Now it moves, and it has reached 90 degrees. It crossed 90 degree. So what should we conclude? Yeah, theta varies from 0 to pi. So this will be the area of the cardioid. Now the last question, what is the value of r? In Cartesian, I used to ask what is the value of y in terms of x. Similarly, in polar, I will keep on asking what is the value of r in terms of theta. Yeah, this one. So let's plug in that value. So you get theta equal to 0 to pi, because this 2 and 2 will get cancelled. And instead of r square, we plug in a square 1 minus cos theta the whole square d theta. And that will be integral theta equal to 0 to pi. I'll take this a square outside. And what is a minus b the whole square? A square minus 2ab plus b square. And I think you know how to integrate cos square theta. If not, I'll give you two formulae. Please note the formulae. Cos square theta is 1 by 2 into 1 plus cos double the angle. And similarly, not in this problem, maybe in some other problem you might need this, half into 1 minus cos double the angle. And that will be, let's start integrate. No, we cannot integrate this. So a square theta equal to 0 to pi 1 minus 2 cos theta plus 1 by 2 1 plus cos double the angle d theta. Now I wanted to open the bracket over here. So we get a square integral theta equal to 0 to pi. Okay, now look at this. 1 and this will make it 1 by 2. So 1 plus 1 by 2, that is 3 by 2. The remaining will be same, minus 2 cos theta. And look at this, this goes inside and creates plus 1 by 2 cos 2 theta d theta. And that gives me a square. Now let's start integration. So 3 by 2 into theta, I think I'll settle that here itself, minus 2 into cos theta, the integral is sin theta, 0 to pi, plus 1 by 2 sin 2 theta the whole divided by 2, 0 to pi. Okay, the good news is you can use the calculator. If you don't know the value, you can use the calculator. Sin 180 is 0, sin 0 is 0. So this is gone. And similarly, sin 2 pi is 0, sin 0 is 0. So this is gone. So only remaining part will be here. So a square 3 by 2 and then pi. So what's the area of a cardioid? 3 by 2 pi a square. So I hope you understood this. Okay, so let's try one more question. Okay, now let's combine our circle and cardioid. So please write the question. This is very interesting. Find the area between the circle r is equal to a and the cardioid r is equal to a into 1 plus cos theta. Okay, now look at this. What's the first thing to do? Yeah, we have to make the initial line. And then what we do is we make the circle and we make the cardioid. But do you remember in Cartesian I told you something? Whenever they give you two different curves, the first thing to do and the best thing to do is solve the equation so you know the points of intersection. And to solve the equation, what should you do? Yeah, you take the value of r here and put it over here. So we get a equal to a into 1 plus cos theta. And that gives me 1 equal to 1 plus cos theta. And that gives me cos theta equal to 0. So theta will be pi by 2, 3 pi by 2, 5 pi by 2, etc. etc. That means the circle and the cardioid intersect at 90 degrees and 270 degrees. So time to draw. So let's make that 90 degree first. I'll use a different color. So here we go. This is our 0 degree. and this is our 90 degree. And let me make 270 degree also. I'll take another vector, 0 degree. We should always move in anti-clockwise direction, 180 degree, and this is our what you call 270 degree. And now we are supposed to draw the cardioid. Cardioid will be in this format towards this side. And where is our circle? Our circle should intersect here, and it should go through the midpoint of this. Not that good in drawing, but I'll repeat once more what I did. So we have the cardioid. I'll repeat, the cardioid is towards this side, and this length is actually 2a, so the cardioid should come somewhere here. It will be more easier. Okay, so look at this. This is a picture. It's a rough picture. You can use some software and make a very good picture. Anyway, this is the required area. I think you can see the required area, and as before, it's a symmetric one. That means the area above the initial line is the same as the area below the initial line. Or in other words, if you know the area above the initial line, you multiply by 2 and you'll get the total area. So please write required area equal to, now look at this, this is very interesting. Anyway, one thing is fixed, the angle varies from 0 to pi by 2. Don't think about the portion below the initial line, because I'm going to adjust like this, 2 times area above the initial line. Okay, and that will be 2 times, if you consider the cardioid, you're going to get this much area. I'll draw that for you with the help of a vector. You'll get this much area. If you use the cardioid, you'll get this much area. I think you're able to see the area moving. You'll get this much area. The whole thing from pole to this much. At the same time, if you use a circle, you'll get only this much area. So it is obvious the required area will be area using cardioid minus area using circle. Once more I'll show you. If I use the cardioid, I'm going to get this whole area. Look at this. I'll use my radius vector. I'll get the whole area covered. At the same time, if I use the circle, I'll get only this much area. So the required area will be area using cardioid minus area using circle. So that will be 2 times, what's the formula? Half integral r square d theta minus half integral r square d theta. It looks the same, but it's not the same. Here what we write is we use cardioid, and here what we write is we use the circle. Okay, now tell me, I'll write in the next page, this 1 by 2 will come outside and this 2 will get cancelled. So I'm going to write very clearly, theta varies from 0 to pi by 2, and I told you in the first one you have to use the cardioid. So I'm going to use a square into 1 plus cos theta the whole square d theta minus, in the second one, it's the same limit, it's the same thing, but I had to use the equation of the circle. That is a square, r is a square d theta. Okay, once more I'll tell you for those who didn't understand. If I use the cardioid, look at this, I'll get the entire area, this much. I'll get this whole area, this whole thing. At the same time, if I use the circle, I'll get only this much, the circular portion, only this much. So what will be the area in between this area? Cardioid minus circle. Now this is simple integration. You have something common here, a square, and the integral is also common. So I'm going to take a square integral theta equal to 0 to pi by 2 1 plus cos theta the whole square minus 1 d theta. I skipped a few steps, but it's easy enough to understand. And you can expand this, and 1 will get cancelled. I'm going to skip that step also. So you end up with 0 to pi by 2, 2 cos theta plus cos square theta d theta. I hope that's fine, because this will be 1 plus 2 cos theta plus cos square theta minus 1 will get cancelled. Now the good news is the limit is from 0 to pi by 2. So we can apply our shortcuts. So this will become 2 into sine theta 0 to pi by 2. At the same time here we can apply reduction formula because it's from 0 to pi by 2. So I write 2, 1. I think you have watched my shortcut in the last few videos. If not, you can watch area 1 and area 2. You will find the shortcut repeated many times into pi by 2. So that gives me, this is going to be sine 91 minus 0. So this will be 2 plus pi by 4. So that's it. So this is the area between circle and parabola. So friends, I'm going to wind this video right now. I'll be back with more. So till then, my friends, bye.